boys and girls. Today we're going to talk about chemical reactions. This follows up the unit where we actually talked about different atoms bonded together with the ionic and covalent bonds. And now that we've got one or two atoms bonded together, we got to see what happens as a product. Okay, so we're looking at the entire process and not just the bond itself. Anyways, you should remember that a chemical change occurs when the substance present at the beginning is changed into something new. And what that means is we are going to break down some bonds that occurred within the first compound. We are going to rearrange those atoms, and then we're going to form new bonds, and those new bonds are going to create compounds that have new properties. And that's our goal for today. And if you look at the example, we've got a picture here of a mixture of hydrogen, so H2. Actually, it looks like these guys are H, so H2, H2, H2. And oxygen, so O2, and O2, and O2. And you guys should remember that those are diatomic. And basically, when we go through and we burn either oxygen or hydrogen, they're going to combine together and form H2O. H2O molecules. So our goal is to go through and look at the idea of an entire reaction happening and not just looking at one single molecule or one single molecule. Okay. And again, you should remember from back in the day that we have 6 signs that chemical reactions are occurring. The idea of gas forming, a solid forming, the release of energy or a temperature change, changing color, something burning, or a different smell. Okay. And then, of course, our examples are things that we looked at during Unit 1. And you should understand those. If not, I would go back and I would look at them. In terms of a chemical reaction itself, all chemical changes, every single chemical change example we looked at was the result of a chemical reaction occurring. Okay? So this happens again when you make or break bonds, and I hate to use that order. It's basically when you break and then rearrange and make new bonds. Okay? So we're rearranging the atoms themselves, and you're going to get one set of compounds. The reactants, that's going to be the things you start with, are going to form a second set of compounds after they are rearranged. Okay? And then we're going to go through and the things that you rearrange into are going to be called the products. Okay? And we'll spend the rest of this PowerPoint going through and looking at that a little more in depth. And why this is so important is because of the law of conservation of matter. Basically, we know that when we're talking about chemical equations, we know that the law of conservation of matter is basically saying that matter cannot be created or destroyed. Okay? It can only change forms. So we cannot go through and lose atoms. We cannot gain atoms. What we're going to do is we have to make sure that the amount of atoms that we start with is going to be equal to the amount of atoms that we end with. Okay? So the number of each type of atom on the reactant side must be equal to the same type of atom on the product side. So if I start off with 42 atoms of gold, I've got to end my whole equation with 42 atoms of gold. And obviously we're not going to get into numbers that are this large. They're generally going to stay under 10. Okay? But you should understand the concept that if we start with 42, we're going to end with 42. I can't make new gold and I can't destroy gold. Okay? So something has to happen to it. All right? And before we got to look into reactions, we got to look at exactly what a chemical formula looks like and what all those numbers mean. Okay, so for the starting, our subscript here for our H2O tells us how many of one single atom we have. So in this case, if we're looking at just this is telling us that we have 2 hydrogens and we've got 1 oxygen. Okay, so this subscript tells us we have 2 hydrogens. Because there's no subscript here, it's an invisible 1, and that means we've got 1 oxygen. This 3, on the other hand, is a coefficient, and it tells us how many of that entire molecule we have. So if this again was H equals 2 and O equals 1, this whole thing is saying that I have 3 of this. So I've basically got 3 times 2. So really I've got, in this 3H2O, I've got 6 hydrogens. And I've got 3 times 1 oxygen, so I've got 3 oxygens. Okay, so the subscript goes through and only counts on that one singular atom that's following. The coefficient is going to go through and it's going to translate itself or transfer itself to every single individual atom within that compound until we hit a plus sign or the end of a parentheses. Okay. So what we're going to do is we're going to try out a couple of these. Work your way through these four, and see if you can figure out how many of each individual atom we have, how many hydrogens and how many oxygens. So I'll walk you through one. You should hit a pause, and then you should try the other three. So for instance, this 2 is kicking over to the H, and it's kicking over to the O. So I'm going to take 2 times the 2 hydrogens. That means I've got 4 hydrogens. And I've got 2 times the 3 oxygens. 2 times 3 gives us 6 oxygens. I would go ahead, I would pause it, and I would work through the next 3. So now that you've attempted the next 3, let's walk through them. This 4 is going to kick through to the iron. So 4 times 2 gives me 8 irons. And this 4 kicks through to the oxygen. So 4 times 3 gives me 12 oxygens. Okay. The 6 is going to kick through to the Na. And the 6 is going to kick through to the Cl, and because both of them have a subscript of 1, it's just 6 times 1, so there's 6 NAs and 6 Cls. And because there's no coefficient to this, I've just got a singular N, and I've got 2 oxygens. Notice that the 2 does not transfer over to this nitrogen. The 2 is solely on that oxygen. Okay. So basically, if you can do this, this is going to be 1/2 of the balancing equation. You just have to figure out how to make sure that the numbers on both sides match up. So looking at equations, we're going to go through and we're actually going to try to balance it. And in order to do that, there are a couple quick tips that we need to go through and figure out. Number 1, in order to go through and in order to conserve atoms, you must balance the number and type of atoms on each side. So for instance, with a CH4 and a 2O2, I've got 1 C, I've got 4 H's, and I've got 4 O's. And on the right side here, I've got 1 C, and I've got 2 O's here, plus the 2 O's here, plus the 2 O's there, plus 4 H's. So I've got 4 H's, I've got 1 C, and I've got 4 O's. And the only way that that was made possible was by adding coefficients in certain places. Okay, I can't change an oxygen atom, but I can have 2 oxygen atoms. I can't change a given water molecule, but I can have 2 of them. So changing the number of how many molecules you have is totally doable. Changing the actual molecule itself, totally impossible. And we'll talk about that soon. All right. So things that you need to know before we move on: reactants are going to be on the left, and products are going to be on the right hand side, and generally we go through and we use an arrow as that middle splitting ground. Okay. In this class we're going to go through and all of our arrows will be pointed to the right. Once you get further into chemistry, you'll realize sometimes they can point in both directions, but we'll lay off that for now. Symbols that show us what's happening. This addition sign means basically we could say plus or added to or mixed with, and all that means is that you're going to throw that into the equation. And forms, produces, or yields are all basically saying equals in math class, so that's where we use the arrow. And if you happen to see a G, an S, an L, or an AQ next to a given element, that's basically just saying that that thing is a gas, that thing is a solid, that thing is a liquid, or that thing is an aqueous solution. So for instance, if I had H2, I may go through and do something like that. And all that's saying is that hydrogen is a gas. So hopefully that doesn't confuse you. We won't use those as much in this class, but you may see them. Okay. So let's go through and actually look at water itself. Does this guy look balanced? No. When we look at each side of this, we notice that we have 2 hydrogens over here, we've got 2 oxygens over here, but on the right side of our equation, the products, we've only got 2 hydrogens and 1 oxygen. So our oxygens are not balanced out. So what do we do in order to try to fix that? Well, the only way that I can add an oxygen to this right side is by adding a whole second water molecule. And the way that I do that is by go through and adding a coefficient of 2. So now I have 2 water molecules, which means my oxygens, I've got 2 oxygens on each side. That's totally happy. The problem is now I have 4 hydrogens on the right, while I only have 2 on the left. So how do I go through and fix that? I can't cut this water molecule in half, but I can double the amount of hydrogen or H2 molecules that I have on the reactant side. So I would do that by adding a coefficient right there. And when we flip to the next slide, you're going to notice that yes, there's a coefficient of 2 there. So I happen to have 4 hydrogens on that side. On my product side, I have 4 hydrogens. I have 2 oxygens on the reactant side and 2 oxygens on the product side. Okay, and we're going to continue practicing these out for the next couple minutes. All right. In terms of the big overall ideas, you can never, ever change a subscript. If I have water, I need to keep it as water. I can't suddenly change and say, hey, I want to add an oxygen and add a 2 there. That doesn't work. The only way that I can go through and actually add a given atom of oxygen is by adding a coefficient. So if I want another oxygen here, I've got to add a 2, and that's going to double not only my oxygens, but it's going to double my hydrogens as well. I can't change the chemical composition. I can change how many individual molecules are involved within that reaction on the side of the equation. Okay, so in terms of going through and trying to work our way through this easily, basically count the number and type of each atom on both sides. If there are different numbers of atoms on each side, you must add a coefficient, and we'll continue to talk about that to change the number of atoms. And then figure out the number by multiplying each compound in order to make the compounds add up. Basically, you want to go through and try to figure out what's the lowest common denominator that is going to make the number of atoms on the reactant side and the number of atoms on the product side equal out. Okay, so let's try this out. Now, realistically, everything I give you is going to come, and I like drawing a line there to kind of show you a breaking point, but I'm going to do everything in T-charts. Okay, so I've got magnesium and I've got oxygen. On the left side here, I have 1 magnesium and I have 2 oxygens. On the right side, I have 1 magnesium and 1 oxygen. And again, the only place that I can go through and actually put stuff is at a coefficient in front. So my first thing I got to think about is, can I go through and balance out the magnesiums? No, they're already set. Can I go through and balance out the oxygens? Yes, they need to be balanced. I need to double the right side. So in order to double this right side, I put a 2 there. And in order to put that 2 there, I have doubled my oxygens, but I also doubled my magnesiums to 2. So now my oxygens are happy, but I need to double my magnesiums on the reactant side. And I do that by going through and adding a coefficient of 2. And so now I have 2 magnesiums and 2 oxygens on each side, and this is a balanced reaction of 2, an invisible 1, and 2. Okay? And again, you can double check them by going through and filling out that T-chart all over again. Alright? So, we'll walk through it, but they're balanced out. We do our T-chart, go through and add the coefficient of 2, and that doubles these numbers. Then we add our coefficient of magnesium, boom, our 2's are doubled out. So this is the exact same thing we just did. So let's go through and try out a couple gems with this guy. Okay, my T-chart, I've got a C and a Cl. On the left here, I've got 1 C and 2 Cls. On the right side, I've got 1 C and 4 Cls. So my C's are happy. I need to find a way to double my Cls on the reactant side. That just doubled them. 2 times 2 gives us 4. And I've got 1 and 4 on the left and 1 and 4 on the right. So that guy is a 1, 2, 1 reaction. And our final one here, and this will be about as tricky as we really get to in day 1, I've got aluminums and oxygens. I've got 2 aluminum, 3 oxygen, 1 aluminum, and 4 oxygens. So if I had this, the way that I would go is I would try to take care of your confusing one. I know that my oxygen's 3 over here and 2 over here, and the lowest common denominator is 6. So how do I get them each to 6? If I go through and I put a 2 in front of this, it turns that into 6. And again, it changes my ALs to 4. So I got to worry about that one later. But I put a 3 in front of the oxygen on the product side, and that turns that into... That was a mistake. There should have been a 2 initially. My bad. I was saying 2, I wrote down 4. Whatever. I throw that 3 in front of it, and that gives me 6 overall. Okay. So the only thing I've got right now, my oxygens are even, and again, that's because I found the lowest common denominator between this guy and this guy. And then the only thing I need to do is balance out my aluminums. And if I've got 4 on my reactant side, I need to have 4 on my product side. Throw a coefficient of 4 in front, and I'm happy. Alright? So hopefully that walks you through how to balance reactions. We'll go through and we'll continue with this in class over and over and over, but this is going to be the main baseline of what we do for the next unit. We'll do it again when we talk types of reactions and energy involved in reactions, kids.